video is based on logical addressing in IPv4 format. Basically, this is a class assignment given by our faculty in the course Network and Communication, coded CSE 1004 in VIT University. So let's begin. So the lecture starts with the definition of IPv4 address. An IPv4 address is a 32-bit address that uniquely and universally defines the connection of a device to the internet. Any device, being a computer or a router, which needs to be connected to the internet, should have a valid IPv4 address. So, as mentioned earlier, IPv4 addresses are unique and universal and are 32-bit long. This gives IPv4 format the address space of 2 to the power 32, which is around 4 million. The IPv4 address has been notated by two notations, the binary notation and the dotted decimal notation. This here corresponds to 8 bits and is called an octet. Similar for the rest of them, these correspond to 32 bits and form an IPv4 address in binary notation. Similarly, the number given here is representation of a IPv4 address in dotted decimal notation. Moving on. So here we have to change the following IPv4 addresses from binary notation to dotted decimal notation. So for these two examples, we just replace each group of 8 bits. The group of 8 bits is replaced with its equivalent binary decimal number, and dots are added for separation. That is, these 8 bits correspond to 129. Again, these 8 bits correspond to 11, same for them, and this one is 239. So these are converted to the equivalent decimal number and are separated by dots. So the name dotted decimal. Moving on. So here we have to do the reverse process of what we did in the last slide. Dotted decimal notation to binary notation. Same as we did there, we have to replace each decimal number with its binary equivalent. 111 is changed with its binary equivalents, 56 is again changed, 45 is again changed, and 78 is again changed. Same for the next example. Now we come across the format in which there are no errors in IPv4 addressing. So if we look at the first example, which is given as 111.56.045.78, in this question there must be no leading zeros. The format should not consist of a leading zero in any of the octets, so this is invalid. In the next example, we come across that this corresponds to 5 dotted decimal integers, that is 5 octets, 40 bits. 5 octets equivalent to 40 bits, which gives us that this is an invalid IPv4 address. If we put here all the 8 bits as 1, we will find a number corresponding to 255 in the decimal system. So the number 301 is an invalid IPv4 addressing system. So now we move on to the next slide. Here we have classful addressing. So in IPv4 format, we come across two types of addressing, the classful addressing and the classless addressing. So in classful addressing, the address space is divided into 5 classes. That's class A, B, C, D, and E. So if we want to differentiate each and every class with the other ones, so we come across with, in binary notation, if the first bit is 0, it belongs to class A, 1 followed by 0 class B, 2 ones followed by 0 class C, 3 ones followed by 0 class D, and the 4 ones, if there are 4 ones, this belongs to class C. For dotted decimal notation, if the first byte means the first octet comes across 0 to 127, it belongs to class A, 128 to 191 class B, 192 to 223 class C, 224 to 239 class D, 240 to 255 class C. Moving on to the next slide. Here we need to find the addresses. We need to find a class of each address. For example, if we take this question point A, the first bit is assigned as 0. So this is the basic answer, class A. If the first bit is 0, it belongs to class A. The first two bits are 1. For the second question, the first two bits are 1 and the third bit is 0. So here we look, the first two followed by 0 is class C. So this is class C. For dotted decimal notation, we have the first octet as 14. So this belongs to class A. 252 belongs to class C. Moving on. Classes and blocks. In classful addressing, we come across a term called waste. As we can see, if we have an address size of 256 and the number of blocks are this much, around 2 million, so we come across wastage of class address space. That is, if we have this space address of 252.0.0.1 and the rest of the remaining addresses 252.5.15.111, the rest of the addresses which are followed by the previous one are unused. So this come across that we waste a large part of address space in the block system. Moving on, the structure of IPv4 addresses. So in IPv4 addressing, the structure consists of two parts, the net ID and the host ID. For class A, B and C, we can calculate the net ID and the host ID as for class A if all the first 8 bits are assigned to 1 and the rest of them are not assigned 1 or 0, basically 0. So the first 8 bits are considered as the net ID and the remaining bits are the host ID for the given address. For class B, the first 16 bits need to be 1, the rest are the host ID. Class C, the first 24 bits means the 3 octets need to be completely 1. Mask. For mask, we say that if we assign the first 8 bits as 1 and take the remaining bits as zeros, the net ID is converted to network mask. Similarly, for class B, if we take the first 16 bits as 1 and the remaining zeros, the network mask is said to be of class B. Similarly, for class 3, the first 24 bits or the 3 octets if assigned 1 and the remaining 8 bits are 0, so the network mask is of class C. And the class ID for these will be 8, 16 and 24 respectively. So uses of IPv4 addresses, there are two uses. We can either subnet them or use for supernetting the IPv4 addresses. So in subnetting, if we divide a large address block into smaller subgroups, it's called subnetting, and we can use a flexible network mask in subnetting. Supernetting, exhaustive classes are A and B address space. Use demand for class B address space because the address space in class B is much higher than class C. To combine several contiguous address spaces into a large single address space. We'll see that moving forward. Classless addressing. So as I told earlier, there are two types of addressing in IPv4 format, the classful addressing and classless addressing. So now we come across classless addressing. So to overcome the depletion of address space, we introduced a new method called classless addressing. There are some restrictions over the benefits of classless addressing. The addresses in the block must be contiguous, means the addresses should be followed by either zeros or ones. The number of addresses in a block must be a power of 2. the first address must be evenly divisible by the number of addresses. So we'll see an example to understand the restrictions for moving further the mask. It consists of n consecutive ones followed by zeros, and n can be any number between 0 and 32. So some tips are there given. In IPv4 addressing, a block of address can be defined as x.y.z.t. This is basically the dotted decimal system followed by the n, in which the x.y.z.t defines one of the addresses and the /n defines the mask. The first address in the block can be found by setting the rightmost 32 minus n bits to 0, and the last address in the block can be found out by setting the rightmost bit 32 minus n bits to 1s. The number of addresses in the block can be found by using the formula 2 power 32 minus n. So in this example, let me write it to the figure first. This is a figure that is a block of 16 addresses granted to a small organization. So here the first address and the last address need to be calculated. So we can see that the restrictions are applied to this block. The addresses are contiguous. The number of addresses is the power of 2. That is 2 power 4 equals to 16, and the first address is divisible by 16. The first address, when converted to a decimal number, is this much, which when divided by 16 results in 215.2024.210. So this thing is obviously of no use. Now if we move on to this block, the first address here is given as 205.16.37.32. The last address is given 205.16.37.47. This means that this block consists of 16 addresses between .32.47. So if we move forward, a block of addresses granted to a small organization. We know that one of the addresses is this. If we have given address, what is the first address of the block is need to be calculated. The binary representation of the address, given address, is this, and if we set the 32 minus 28, that is the rightmost bit to zeros, we get the following binary equivalence representation, or if we convert that into the dotted decimal notation, we get the address as 205.16.37.32. This is actually the block shown in figure 19.3. This is the block actually shown in figure 19.3. This is the block which is calculated from here. Okay, now move on. So similarly for that example, this block only we calculate the last address. That is, we set the 32 minus 28 means the 32 minus n rightmost bits to 1, we get the last address of the block. Now moving on. So we need to find the number of addresses in the example 19.6. Example 19.6. This is example 19.6. Here we know that n is 28. So if we move to the question, the value of n is 28, which means that the number of addresses is 2 power 32 minus 28, or 2 power 4, which is 16. So here we are given another way to find the first address, the last address, and the number of addresses by using the mask given. So this is particularly useful when we are writing a program to find these pieces of information, that is the first address, the last address, and the number of addresses. So for example 19.5, the /n or the mask given was 28. So the 28 can be represented as this, that is 28 ones and 4 zeros in the binary equivalence format. So we need to find the first address, the last address, and number of addresses. So for the first address, The first address can be found by ANDing the given addresses with the mask. ANDing here is done bit by bit. The result of ANDing two bits is 1. If both are 1, the result is 0 otherwise. So we have given the address is given to us, the mask is need to be ANDed with the given address, and we will find the first address of the block. For the last address can be found by ORing the given address with the complement of the mask. That is, we need to complement the complement the network mask first, and then OR the result with the given address, and we will find the last address of the block. The result of ORing two bits is 0 if both the bits are 0. The result is 1 otherwise. The complement of a number is found by changing 1 to 0 and each 0 to 1. The number of addresses. Now for the C part, the number of addresses can be found by complementing the mask. Complementing the mask and adding 1 to it. Special addresses. So we have two types of special addresses, that is the network address and the broadcast address. The first address in a block is normally not assigned to any device. It is used as the network address that represents the organization to the rest of the world. Broadcast address is the last address in a block, is used for broadcasting to all devices on the network. So now routing in IPv4. A router has two addresses. First, an address through which the device inside of a router can be accessed. Another address belongs to the granted block, that is the subnetwork. So here you can see in the figure that the internet is connected to the router, and the router then distributes the network to the subnetworks. Hierarchy of IPv4 addressing. Each address in the block can be considered as a two-level hierarchical structure. The leftmost n bits, the prefix, define the network, and the rightmost 32 minus n bits define the host. So why do we choose hierarchy? So in the given figure we can see that two levels of hierarchy are in a IPv4 address is represented. The first bit is representing the area code, the second one is changing the exchange office, and the third one is changing the subscriber. Two-level hierarchy. The 28 bits given in the previous question define the network prefix, and the remaining 4 bits along with the network prefix give us the host address. For three-level of hierarchy, we see that the network is divided into 3 subnets, and all are connected through one single router which distributes it to the rest of the internet. So you can see that the 26 here for subnet 1, that is 26 bits are the network prefix. The one added here is the subnet prefix along with the network prefix, and the host address is the whole 32 bit. Similarly for subnets 2 and 3, the subnet prefix is changed to 2 instead of 1, and the remaining other are the host address. Here we come across an example which is this figure actually. An ISP is granted a block of address starting with this. The ISP needs to distribute these addresses to 3 groups of customers as follows. The first group has 64 customers, each need 256 addresses. Similarly, the second group needs 128 addresses for 128 customers, and the third group has 128 customers, each needing 63 addresses. So we need to divide this network into subnetworks. So for group 1, this group needs 256 addresses for each customer, and there are in total 64 customers. So this means we need to assign the formula as 8 into log 256 to the base 2, that is 24. The prefix length is 24 for this group, and the first customer has the address 190.100.0.0 till the address of 190.100.0.255. Similarly, the second customer has 190.100.1.0, and the last address for this customer is 190.100.1.255. The prefix length being 24. So for 64 customers, the total number of addresses will be 16,384. So for the second group, each customer needs 128 addresses. This means that 7 into log 128 and base 2 bits are needed to define each host. The prefix length is then calculated to be 32 minus 7 equals 25. So the addresses will be the following. For the first customer, the address will be 190.100.64.0, and the last address for the first customer will be 190.100.64.177. Similarly, for the second customer and the last customer, that is the 128 customer, will have the following addresses. In total, the addresses will be 128 into 128, that is 16,384. Moving on. Now for the last group, we'll have each customer a need of 64 addresses, that is 6 log 64 on base 2 bits are needed to each host. The prefix list is then 32 minus 6, that is 26. So the addresses are, for the first customer, 190.100.128/0 to 190.100.128.63 being the last address of the first customer. Similarly, for the second customer and the last customer, that is the 128th customer, needing the 64 addresses, will be as follows, and the total number of addresses for this block will be 128 into 64, that is 8,192. So now, as we can see, the number of granted addresses to the ISP is 65,536, but the allocated addresses by the ISP is 40,916. That is, we still have plenty of 24,576 addresses unfilled. So that concludes our lecture for the class full and the classless addressing, that is basically the logical addressing in IPv4 format. See you again.